Hello everyone, this is Yingqiang Zhang from Alibaba Cloud. Today I'm excited to present our work, PolarDB Serverless, a shared storage-based serverless database, achieving seamless scale-up and read scale-out. Recently, serverless database has become more and more popular for their high elasticity and pay-as-you-go mode. Unlike traditional provider database, which can only provide fixed resources when the user application demands change. Serverless databases are capable of automatically adjust the resource amount based on users' requirements. Users only need to pay for the resources they actually used, which can lead to significant cost saving and also can avoid the stability risk brought by the unexpected business peaks. Many serverless databases in the market adopt a primary-secondary architecture. In this setup, unlike traditional databases, the primary and secondary nodes share the same cloud storage. This approach eliminates the need for additional storage when scaled out with more secondary nodes. Some of these databases also deploy proxy nodes atop the primary and the secondary for some additional functionalities. The primary nodes create logs for every update, send them to the second nodes, then secondary nodes apply the log to its in-memory date. Since the log application is asynchronous, the second nodes may not return stale date. In such case, read request that request read after write consistency must be processed on the primary node. Although the primary-second-based cloud-native databases are very popular today, the serverless database based on this design is not trivial, still facing some challenges. The first limitation is that the migration of primary node may introduce a period of downtime. When the scale up the primary node by allocating more resources, although in most cases, the resources on the current physical host are sophisticated, but there are some situations in which local resources are not enough for the scale-up. In this case, it must migrate the instance to another host which have enough resources. But the migration usually brings a period of downtime and interrupt the application. Of course, we could also reserve sophisticated resources on each host, but this will load the resource utilization and violate the original intention of serverless. As one of the top serverless database products, we call it Database A, which is widely adopted and shows better performance than others. We use the Database A as an example to show the migration performance. Because it's hard to manually evoke migration, we simulate the migration scenario by promoting a second node to the primary nodes. Since migration typically involves adding a new instance as a second node and then promoting it to the primary nodes. From the test, we can find that the promotion process takes about 15 seconds. During this period, the application loses its connection to the database and can't reconnect until the migration is finished. This is often difficult for users to accept, especially since it often happened during the application's peak activity period. The second limitation is that they do not support read scale-out due to the lack of the strong consistency on secondary node. Typically, it is reasonable to expand the read capability by adding second nodes when the load on the primary nodes increase. But strong consistency is essential for most transactional workloads, and the second nodes only support eventual consistency. They have to offer two endpoints. One ensures strong consistency, and the other provides eventual consistency for the reporting application. In this design, when the read pressure becomes heavier, it has to scale up the primary node rather than scale out secondary nodes. a heavy read workload can scale up the performance to the maximum capability, and the performance cannot be improved anymore, while the scale-out ability of the second nodes are not utilized. We again take database A as an example to test the auto-scaling in the read domination workloads. We added a substantial read-only workload on primary node due to the requirement for the strong consistency. The throughput and the allocated resources are increasing, eventually become stable. We further added additional workload, however, the allocated resources do not increase any further because it has already reached its maximum limitation, and the throughput also have no further improvement. If the system extends its support for the strongly consistency on second nodes, it would have capability to scale out second nodes for handling heavier read workloads. To address these two limitations on shared storage-based database, we propose PolarDB Serverless. PolarDB Serverless is built based on provisioned PolarDB. Thus, it has similar architecture to PolarDB. However, different from other serverless databases, PolarDB Serverless supports the seamless migration mechanism and the read scale-out ability. PolarDB Serverless inherits the strong consistency feature from the provisioned PolarDB. In this case, it can scale out the second nodes to improve the read performance. Each PolarDB Serverless can provide a uniformed endpoint with strong consistency. PolarDB Serverless can effectively scale out the second nodes in the background to maintain optimal performance. PolarDB Serverless also implements the seamless migration to support migrating a database instance seamlessly from one physical host to another without interruptions to the applications. The strong consistent design has been introduced in our another paper, which is published in the last year's VLDB. To achieve strong consistency with low latency, PolarDB tracks the primary node's modification timestamp at 3 progressively fine-grained level, and further design a linear lamp timestamp to reduce the second node's timestamp fetching operation, and leverage the RDMA network for all the data transferring to minimize network overhead and the CPU usage. Our evaluation shows that PolarDB does not incur any notable overhead for ensuring strong consistency read, compared with the eventually consistency that's the stale read. For more detail, please refer to our PolarDB SCC paper. In the next slides, we will focus on the seamless design. In PolarDB Serverless, the proxy nodes are responsible for managing connection access. All applications are directly connected to the proxy nodes. The proxy nodes verify the access rights for the application's connection and estimates a corresponding connection to the database instance for each of them. During the database migration, the proxy node estimates new connection to the new instance, close connection to the old instance after shutting them down. Subsequently, it remaps the application's connection to the new instance. Therefore, the connection between the application and the proxy nodes remain active without any disruption during the migration. Another challenge is the active transaction migration. Although connection maintenance technology can make idle connection remain imperceptible to the application during the migration, connections with active running transactions are difficult to handle. For example, there is one transaction. If the migration happened during the execution of the query 2 in this transaction, after migration, the transaction is interrupted. We need to rebuild and continue to this transaction on the new instance. Because the query 1 has already acknowledged to the application, we need to recover the change made by the query 2 on the new instance. As the query 2 is still being executed when the migration happened, maybe part of the query's change has been persistent to the storage. So we need to roll back the changes made by the query 2 and re-execute it on the new instance. This is a big challenge. The transaction migration requires to recover finished query, roll back, and re-execute the unfinished query with one transaction. To overcome this challenge, we propose the query statement cache on the proxy nodes. The proxy nodes cache the latest query for each transaction, along with its associated metadata. When the proxy nodes receive a query from the application, it initially caches the most recent query for each transaction in this memory, mark it as unfinished. When the database processes this query, it will generate corresponding redo and undo logs for the queries. Once the query is finished, the database will introduce the maximum undo log IDs generated by the current query in the response to the preeminence nodes, which indicate the rollback pointer. When the proxy nodes receive a query's response from the database, it associated its ID with the query and marked the query as finished. So, how do we ensure that the new primary instance contains the latest date? During migration, the old instance will send its redo log to the new instance as a second node before the switchover. At this time, the old instance will double write the latest redo log to the new instance via RDMA. Using RDMA can minimize the impact to the preeminence node and reduce latency. After switchover, the new instance can apply the redo log to recover all undo log and modify the date. After switchover, the proxy nodes will check the unfinished query in its cache and send the request to the new instance to roll back the unfinished query. The rollback is achieved by applying the undo log, starting from the transaction's latest undo log and end at the query's undo log ID. That is stored on the proxy node. After the rollback, the query can be sent to the new instance for execution. Then the transaction can be continued on the new instance. If there is a new transaction arrivals at the proxy node during the migration, it will be also temporarily cached on the proxy nodes and will be sent to the new instance once it's ready. Like many databases, PolarDB Serverless implements multi-version concurrency control and defaults to read committed snapshot isolation. This approach can allow the reads to access the committed version without raw logs, while writes request the exclusive log obeying a two-phase locking protocol. PolarDB Serverless embeds the transaction ID within the raw's metadata upon modification. This is a common practice in many databases, like Oracle or the PostgreSQL. In this mechanism, a transaction intended to modify a rule first check the embedded transaction IDs. If this ID indicates an uncommitted transaction, it means that the rule is logged by another active transaction. During migration, once we finish the recovery in the date on the new instance, the log state should be also recovered accordingly. Finally, we test PolarDB Serverless in Alibaba Cloud environments. We first test the performance of migration and compare to the database A. We again use the secondary promotion to simulate the migration. From the figure, we can find that PolarDB Serverless can finish the migration in half a second, which is 30 times faster than the database A. Additionally, during the migration, there are no aborting transactions in PolarDB Serverless because it supports transaction migration. But the database A reports some abortings, depending on there are how many active transactions at that time. We then test the read scale-out ability of PolarDB Serverless and compare with the database A as baseline. In this test, initially no workloads running, which both PolarDB Serverless and the database A operation on a minimal hardware resources. We used the Sysbench to generate a standard read-write workload with high pressure and begin running at 50 seconds mark. Database A routing all requests to its node due to the strongly consistency remains. We gradually increased the workload, and eventually the performance is substantiated. However, PolarDB Serverless scaled rapidly in response to the workload, showing an immediate throughput rising. Because PolarDB Serverless can scale out second nodes to handle read requests with strong consistency, reaching a peak throughput more than 1 million queries per second, which is 6.5 times than database A. Finally, we show the commercial deployment and the growth trades. Since the official launching of the PolarDB Serverless at December 2022, following the end of the public beta testing, PolarDB Serverless's online commercial deployment instance has already exceeded 10,000 instances. The annual growth rate of the instance scale has exceeded 12 times and still growing rapidly. We believe the serverless model will gradually become the mainstream sale model for PolarDB and for all the cloud-native databases at last. That's all my presentation today. Thank you again.